Okay, so lesson 3, permutations and clones. What is the goal? I want you to be able to solve problems that involve arrangements using identical objects. So if you remember back to a previous example yesterday or the previous lesson, we said no repetition allowed, has to be different colors. Now today I am saying, well, what happens if we do have repeated colors in a question? So my first example, I've gone through and I've done all the arrangements. Okay, I've written out all the different arrangements that exist. And I checked it because I know that if I have 4 objects here, so off to the side I'm going to do a bit of calculation. If I have 4 objects and I use all of them, there should be 4 times 3 times 2 times 1. So 4 times 3 times 2 times 1 gives me a total of 24. So there's 24 possible outcomes if we ignore the fact that there's two E's in that question. So if I go through and I write out all 24 arrangements that I can find, what happens is I find that there's a lot of repetition. So my ABEs, okay, they occur twice. All right, so I don't want them to occur twice. The AEBE, and what happens is I'm not going to go all the way through because it's a little bit on the time-consuming side. Um, what I'm actually going to do, I'll pause it and I'll cancel them out and show you what the result is. So even though you couldn't tell that I actually paused it, you can see I made identified my unique ones, and anything that had a clone I got rid of. So although there was 24 outcomes, there's only a result of 12 remaining. So 12 remain, or 12 unique combinations exist. All right, so you're not going to have to write this out, obviously. I just did it for example purposes. So if I highlight a bunch of stuff here, if I can, I just want to shrink it, and I just want to talk about what happens in this process. So there is 12 unique answers. What happens is that if I have, for example, I'll do it down below here, A, B, E, and I'll use a subscript 1, E, subscript 2 just to show the 2 E's, and I rewrite it as A, B, E subscript 2, E subscript 1, that would count as, according to the 24 possible combinations, that counts as 2 combinations. But if those subscripts weren't there, and you were looking at these 2 written combinations, you'd say they're the exact same. So we end up with what we call a clone. All right, so it's a clone. So in order to calculate this, we need to figure out a formula. And before I give you the formula, I want to look at the next example here. So how many unique arrangements are there using the letters A, B, B, B? So really, you know that there is only going to be a select few, and this one doesn't take too long to write out. It's just moving, if I could write it out properly. So it's just a matter of moving the A through the B's to give us all our combinations. All right, those are the only unique combinations. So there's only, therefore, 4 unique combinations, or 4 unique orders. All right. So how do you calculate this? Because again, we know, since there's 4 choices here, we know that the answer is going to be 24 again. 4 times 3 times 2 times 1 tells me that there should be 24. How do we get it down to 4? Well, what we're doing in each case, and some people might see this, some people might not, in order to calculate it, what we're doing is we're taking the total number of combinations, so 4 factorial for this question up here, and we're going to divide it. In this case, I had 24, I ended up with 12. So I ended up dividing by 2. I'm going to fix that 1 second. Here, 4 factorial again. There's 4 choices. And I divided by something that would give me 4. So just going back or doing reverse order here, divide. The answer is going to be 4. So that means 4 factorial is 24. So I had to divide by 6, which means that I actually divided by 3 factorial. And up here, I divided by 2 factorial to get the 12. Okay? So that is going to be needed for us to move on and get that formula. So here it is, equations for permutations and clones. The formula is n factorial divided by a factorial, b factorial, c factorial, dot, dot, dot. That's where n is the number of objects, total number of objects. Let's go with that. Total number of objects. All right, so it doesn't matter. Clones, individuals, does not matter. A is the number of clones for one object. B is the number of clones for a second object, and so on and so forth. So if that doesn't make sense yet, then the examples will help, and this just continues on for a third object. All right, so the more famous, you see this in all the data management books, and at some point a teacher's can use this as an example. Mississippi is a great one to use for data management. So in order to figure out, excuse me, how many different ways or how many different ways you can arrange the letters, and that should be added to the question, so it makes sense. Determine how many different ways the letters in Mississippi can be arranged. You're going to have lots of repetition there because of the S's and the I's. So we figure out total number of objects here. So n would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I have 11 distinct objects. And what I'm going to do is, I'm going to use the matching variable, I guess. So how many I's are there? Well, there's 1, 2, 3, 4 I's. S's. There would be 1, 2, 3, 4 S's. And I think the P is repeated as well. And we got 2 P's. So if I did that right, that's what it should end up being. So how many combinations are there? Well, there's the total number of objects, 11 factorial, divided by, there are 4 I's, so there are 4 clones, so 4 factorial. The S's, also 4 clones. The P's, there are 2 clones. All right, so it's the number of clones that we use here in the denominator. And what that does, that process eliminates all of our clones when we go to do that calculation. So as I punch it through the calculator, divided by 2, there are actually 34,650 different combinations. 34,650 ways to arrange Mississippi. Okay. So last example, just one more to emphasize it. Mitchell. So in Mitchell, 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 objects to arrange. The L occurs twice. That's it. So that means that we would have 8 factorial over 2 factorial for the number of ways we can arrange Mitchell. So it ends up being 20,160. All right. There you go. That's dealing with clones when you're dealing with permutations. Ways to arrange Mitchell. All right. This usually goes well in this section. It's in the next section when we start dealing with probability that people abandon or forget about the whole clones thing. So it's something that A, I will emphasize in this unit, and B, it's going to come back and visit us in the next. So it's something to be aware of. You always have to be aware of cloned objects because they are quite common. There's the homework. So good luck with that. If you need any help, you know where to find me, and we'll talk to you next day.